In this video, we're going to look at an example of the paired t-test. Doctors compared the peak expiratory flow rate in liters per minute before and after a walk on a cold winter's day for a random sample of 9 people with asthma. The doctors suspect that a morning walk in the cold air will boost each asthmatic's peak expiratory flow rate. Let's do a hypothesis test to determine if their suspicion is justified. And I usually don't provide you with the raw data here, but I thought it would be useful in the context of the paired t-test to see how these differences are computed. Now, so we've got 9 people randomly chosen, and we've got their before values and we've got their after values. So there's our clue that we're doing a paired t-test, yeah, because of those before and after values. And these differences are computed as the before minus the afters. Yeah, this looks like it's before minus the after values. So that's how those differences are computed. Down here, we've got the mean and we've got the standard deviation of more than we really need. I've included this info here kind of as a ruse, because once you've got these columns of differences, you really don't need these values anymore. And we're not going to use the mean of the befores, and we're not going to use the mean of the afters. What we are going to use is the mean of the difference to data. So right there, that's the D with a bar, -56 or so. And right here, this is the standard deviation of the differences. So that's S with a subscript D. Before we go crunching away and creating hypotheses, I have a question to ask you. Suppose we did a Shapiro normality test on the column of differences over here, and we got a p-value of 0.5746. What does this mean? Well, remember that the Shapiro normality test is its own little hypothesis test, in which the null hypothesis essentially is that the data is normal. And I don't even need to think about the alternative here, because this p-value is quite large. And so that would mean we do not reject this null hypothesis written right down there. So that implies that the data is normal. Data approximately normal. And that's going to be an important thing to consider here, because we're doing a t-test, right? And this t-test is going to focus on these differences. So in a moment, I'm going to show you what the requirements are. And it's one of those requirements is that these differences are normally distributed, or that they have a sufficient sample size. But that wouldn't be the case here, because there's only 9 pairs. Okay, let's get on with the paired t-test. Usually, our first step is to verify that certain requirements are met. These requirements are the same requirements we saw for the regular t-test. They have been slightly tweaked to apply to paired data. So the 2 samples must result from a paired design. Check, because we have the before and after situation going on. The differences are considered a random sample. Check. If we cruise up here, we see that word random sampling was used. Great. The observed differences are independent of each other. Let's think about that. If you were one of these subjects in this study and you are getting your peak expiratory flow rate measured before and after a walk, is how you are breathing going to have any influence or dependency upon how someone else is breathing? Probably not. So I think that's a fair assumption to make. And lastly, the differences must be drawn from a normally distributed population. And that's what we did up here with this Shapiro business. So that is check, because the Shapiro p-value was pretty large. It was bigger than any alpha you can consider. Usually alpha is 0.05. If we had the raw data, we would test for normality with that Shapiro test. Yes, yes. But we would probably also look at the QQ plot, because those are really nice to look at. All right, let's look at the next. Let's identify the response variable, and then we'll declare the null and alternative hypotheses. So the response variable, what was measured? That was the peak expiratory flow rate. Null and alternative hypothesis, H0, HA. Our hypotheses are always in regards to a population parameter. So I'm going to write mu with a D. So when we say mu with a D, we're talking about the mean difference in peak expiratory flow rate before and after that cold morning walk. And I probably shouldn't have wrote equals here. Undo that, because we're going to need to look at the hypothesis in the description of the study to see if this is a directional or a non-directional test. But before we get there, we're looking for a difference. And the null hypothesis always states no difference. I'm going to write that over here. HO is always a statement about no change or no effect. And what value represents no change? 0. So the paired t-test always has a 0 right here. Equals, always, for the null. Let's go see if we need a directional or a non-directional hypothesis. I'm going to scroll up a bit. The doctors suspect that the morning walk in the cold air will boost each asthmatic's peak expiratory flow rate. Okay, so they think that we've got the befores and we've got the afters. They think that the after values will be larger, right? So if this subtraction occurred, don't they anticipate these to be mostly negative numbers? Because the afters they suspect will be boosted or larger. Now I'm not looking at the data to validate that. I am basing this on the description of the study. So the before minus the after, since the afters are suspected to be larger, should result in negative values. So I'm going to take this less than symbol and translate it all the way down here. So we are doing a left-tailed alternative hypothesis here because of the way that the differences were computed. Because it was before minus after, and they think the after values will be larger, those would be expected to be negative differences. If these were swapped, then we would have written a greater than sign if the befores and afters were swapped. So this was only an artifact of how these were computed. Next step, let's state the level of significance if we want the type 1 error rate to be 1%. Now we usually have our default alpha, right? Usually alpha is 0.05. But this is not what we're going to use here. We're actually going to use 0.01. Because remember, the type 1 error probability is alpha. So probability type 1 error is alpha. So here I've told it to you in sort of a roundabout way. Next step, let's compute the test statistic. I've got the formula here, the mean of the differences, D with a bar, that was negative 56.11. The standard deviation, about a 34. And the number of pairs, the number of differences is 9. So I'm going to write all those into our formula. Okay, so I've written out our test statistic here, and I have inputted it into R over here. I wrote minus 0 because I was feeling cute, and square root of 9 is 3. Our test statistic, therefore, is negative 4.92. Our next step is going to be using R to compute the p-value. Instead of bopping right into R right now, I'm going to draw a quick pick. This is the t-distribution with, I need to tell you the degrees of freedom. Because we have paired samples and we look at the differences, our degrees of freedom is just n minus 1, where that n is the number of differences. Because we had the two samples, but they were in pairs, and we did the subtraction. We're only focused on those 9 pairs. So our degrees of freedom here is an 8. So this is going to apply to the t-distribution with 8 degrees of freedom. 0 is always in the middle. And gee whiz, our test statistic is a negative 4.92577. And we want the area beyond our test statistic. But remember, this is a left-tailed test, a left-tailed alternative hypothesis. So I really only want the area in the left tail down here. So it's not a two-tailed test where we would end up doing a doubling procedure over here. So we only want the area or the probability in the left tail. So how are we going to type that into R? We want probability. We do not know it. So in R, we need to use PT. I need the probability to the left of negative 4.9257775. I might as well use it all. It's all right there. The degrees of freedom is 8. Okay, so we've got a pretty small probability there between 0.0005777. Okay, now that we have our p-value computed, and I circled it here in yellow, we are ready to state our conclusion to the hypothesis test. I like to ask that we state this conclusion twice. Can we give a more statistical and technical conclusion, and then interpret that conclusion and bring it back into context of the study and the variables that were measured? Here, because the p-value is small, since the p-value is less than alpha, alpha I said was 0.01, and our p-value is certainly less than that, our conclusion is going to be, when the p-value is low, the null must go. Reject the null hypothesis. Now let's interpret that back into the context of the study. So I'm going to scroll back up to our hypothesis so we can think about what this rejection implies. Remember, we are not proving anything, but our data may support a hypothesis. And because we are rejecting the null, that means that our data has support for the alternative. And the alternative essentially states, we need to translate these symbols, that the mean difference in the peak expiratory flow rate before and after the cold walk is negative. Or we can say that the mean in the peak expiratory flow rate was boosted after the cold morning walk. Something to that extent. But I do want to mention the mean. So I'm going to write some of that down. So the data provides sufficient evidence that the mean difference in the peak expiratory flow rate, and it might be worthwhile mentioning that that difference was calculated as before minus after, is negative. Now that's still a little technical because is negative, that's kind of a little weird to think about. You might even want to say that the mean peak expiratory flow rate was indeed boosted after the cold morning walk. We just want to get that point across there. So hopefully this was useful to see an example of the paired t-test. A quick run through here. I'm going to scroll back up to the top. In a paired design, we do not look at the individual observations. Once we have calculated those differences over here, those are what get analyzed. We want the mean of those and the standard deviation of those differences. Because it's still a t-test, we still have kind of this laundry list of requirements or assumptions that need to be made. After that, it's a t-test through and through. We have a null and alternative hypothesis that is about a mean. There is a test statistic, which then determines a p-value. The way that p-value is computed is based on the direction of that alternative hypothesis. And then we state our conclusion based on that p-value.